Hello students, now let's move on to next theorem. If f belongs to R of alpha, then Cf also belongs to R of alpha, where C is any real number. Also show that integral a to b Cf d alpha is equal to C into integral a to b f d alpha. So in the first part of the theorem, I need to prove Cf belongs to R of alpha if f belongs to R of alpha. And in the second part, I need to prove integral a to b Cf d alpha is equal to C into integral a to b f d alpha. Okay, now let's get into the proof. Given f belongs to R of alpha, to prove that Cf belongs to R of alpha, where C is any real number. So there exist three cases: C equal to 0, C greater than 0 and C less than 0 if C is a real number. Okay, now case 1. If C is equal to 0, then Cf is equal to 0 into f, which is equal to 0. It's a 0 function. See, I am multiplying this real number 0 to some function f. So that becomes a 0 function. Okay, so 0 function which is continuous on closed interval AB. So 0 function is always continuous on closed interval AB. Okay, it is continuous on all interval. Okay, we know that every continuous function on closed interval AB belongs to R of alpha. So here we have done this theorem in previous videos. Okay, so every continuous function f on closed interval AB is Riemann-Stieltjes integrable. So it implies Cf is also Riemann-Stieltjes integrable because Cf here is a 0 function which is continuous. And now let's move on to case 2. If C greater than 0, see, f belongs to R of alpha implies f is bounded. Okay, f is bounded on closed interval AB. So for f to be Riemann-Stieltjes integrable, this is the necessary condition. Boundedness is the necessary condition. And if f is bounded, then obviously Cf is also bounded, where C is greater than 0 is any real number. Okay, so since f is bounded, Cf will also be bounded on closed interval AB. Now let's consider partition P, which is equal to x0, x1, etc. up to xn, where x0 equal to a and xn equal to b, be any partition of closed interval AB. Okay, see here, since f is bounded, Cf is also bounded, then there exists infimum and supremum. Okay, so since there exists infimum and supremum for both f of x and Cf of x, as both are bounded, let mi, small mi, be the infimum of f of x for all x belong to this interval xi minus 1 comma xi, and capital Mi be the supremum of f of x in the same interval, and mi dash be the infimum of Cf of x in this interval, and capital Mi dash be the supremum of Cf of x in the same interval xi minus 1 comma xi. Now Mi dash is actually the infimum of Cf of x for all x belong to xi minus 1 comma xi. And here, if I take the C outside, I can have C into infimum of f of x because C is constant and also C is positive. But this is not the case if C is negative. Okay, so here, since C is positive, I can take this outside. So C into infimum of f of x is nothing but infimum of C into f of x. So both are one and the same. And we know that infimum of f of x is nothing but small mi. So I can write mi in place of infimum of f of x. So mi dash is now equal to C into small mi. Okay. Similarly, capital Mi dash is equal to supremum of Cf of x. or if I take this constant c outside, I have c into supremum of f of x because c is positive here. So this doesn't affect the supremum even though if I take the c outside. Okay, so c into supremum of f of x, and in place of supremum of f of x I can write capital Mi because I have taken this capital Mi as supremum of f of x in the interval xi minus 1 comma xi. So Mi dash is now equal to c into Mi, capital Mi. So now consider the difference u of p comma cf comma alpha minus L of p comma cf comma alpha, because if I show this difference less than epsilon, then cf belongs to r of alpha. Okay, so now I have considered this difference. Okay, so according to the definition, summation I equal to 1 to n capital Mi dash, because capital Mi dash is the supremum of CF. Okay, so capital Mi dash minus small mi dash. Small mi dash is the infimum. Okay, infimum of CF in the interval xi minus 1 comma xi. So I have taken this delta alpha I common, and instead of 2 summation I have 1 summation. Summation I equal to 1 to n mi dash minus small mi dash into delta alpha I. Okay, and in place of mi dash and small mi dash I will write c capital Mi and c small mi. Okay, so here I have summation I equal to 1 to n c mi minus c small mi into delta alpha I. Okay, so in place of mi dash I have this, and in place of small mi dash I have this, and that is equal to, see, if I take the c outside, see, this is constant, it has nothing to do with the summation, so I will take this outside the summation and I will write the remaining thing here, and this is nothing but u of p comma f comma alpha minus L of p comma f comma alpha with this c outside. So name this as 1 because I have another case for c. Okay, for c less than 0 is the another case. Okay, if c less than 0, what happens? Then mi dash, which is equal to infimum of cf of x for all x belong to this interval, is equal to, see, if I now take this c outside this infimum, it nowhere remains as infimum because c is a negative real number. C is less than 0. Okay, c is less than 0. So if I take the c outside, this infimum will now turn to supremum. So supremum of f of x, and when multiplied with this c, will be equal to infimum of c f of x. Why? Because c is negative here. So you need to be very careful. You can take one example and try, you will get this. Okay, so infimum of cf of x will be equal to c into supremum of f of x. Why? Because c is negative here. And what is supremum of f of x? It is nothing but capital Mi, because I have taken capital Mi to be the supremum of f of x. Similarly, capital Mi dash is equal to c into small mi for all I see here. Why? Because small capital Mi dash is equal to supremum of cf of x. And if I take the c outside, the supremum will become infimum. Why? Because c is negative here. So infimum of f of x when multiplied with this c gives you supremum of cf of x. Okay, and this infimum of f of x is nothing but small mi. So I have written capital Mi dash is equal to cmi. Okay, now if I take the difference between the upper sum and lower sum of c of f with respect to the partition p, I have u of p comma cf comma alpha minus L of p comma cf comma alpha is equal to summation I equal to 1 to n capital Mi dash minus small mi dash delta alpha I. And using the values of capital Mi dash and small mi dash, I have summation I equal to 1 to n c mi minus c capital Mi delta alpha I. If I take the c outside the summation, I have summation I equal to 1 to n mi minus capital Mi into delta alpha I. Okay, this Mi into delta alpha I with this summation is nothing but the lower sum of f with respect to p minus capital Mi into delta alpha I with this summation is nothing but u of p comma f comma alpha, which is the upper sum of f with respect to the partition p. So if I take the minus sign outside, I have u of p comma f comma alpha minus L of p comma f comma alpha, okay, with the minus c. Or if I take this minus this side, I have minus of u of p comma cf comma alpha minus L of p comma cf comma alpha is equal to c into u of p comma f comma alpha minus L of p comma f comma alpha. So name this as 2. So from previous case that we have that equation 1, and this case I have named this equation as 2. So now from 1 and 2, mod of this is equal to c of u of p comma f comma alpha minus L of p comma f comma alpha. See why? Because here I have minus of u of p comma cf comma alpha minus L of p comma cf comma alpha equal to this, and in the previous case I have plus of u of p comma cf comma alpha minus L of p comma cf comma alpha equal to this. So from 1 and 2 I will just write mod. Okay, so from 1 and 2 I have mod of this is equal to c into u of p comma f comma alpha minus L of p comma f comma alpha. So this mod covers both plus as well as minus. So equation 2 as well as equation 1 is covered in this single equation now. Okay, and since f belongs to order of alpha, for any epsilon positive, there exists a partition P of closed interval AB such that the difference between the upper sum and lower sum is epsilon by C. See why this epsilon by C is, we have the C here. Okay, see here, this which I have named this equation as 3. Okay, so 3 now implies mod of this is less than epsilon by C into C. Okay, so this C will now get cancelled with this C. Okay, so I am now left with this mod of u of p comma cf comma alpha minus L of p comma cf comma alpha is less than epsilon. So if mod of this is less than epsilon, then obviously u of p comma cf comma alpha minus L of p comma cf comma alpha is less than epsilon. Okay, see here, this mod of this is less than epsilon means both it is for plus of this as well as minus of this is less than epsilon. That is, CF belongs to order of alpha in both the cases 2 and 3. That is, whether if C is less than 0 or C is greater than 0, this holds. Okay, so CF belongs to order of alpha. So this is all about the first part of the theorem. Now we'll move on to the second part of the theorem. Okay, now to prove that integral a to b c f d alpha is equal to c into integral a to b f d alpha. Case 1, if c is equal to 0, obviously this also will get 0 and here also will get 0. So integral a to b c f d alpha is equal to c into integral a to b f d alpha. So LHS equal to RHS if c is equal to 0. Suppose if c is greater than 0. Now consider the upper integral. Okay, upper integral of CF d alpha. Now according to the definition of upper integral, this is equal to infimum of all u's of CF with respect to the partition P. Okay, so I am taking the infimum of all upper sums. So here P can be any partition. So I am taking the infimum of all upper sums. Okay, and now if I take this C outside, since C is positive, it doesn't affect this u of p comma f comma alpha. See here, simply C into u of p comma f comma alpha is nothing but u of p comma cf comma alpha. Okay, why? Because C is positive here. So C into u f comma alpha is nothing but u of p comma cf comma alpha. So infimum of this is infimum of c into u of p comma f comma alpha. See, the c is constant. I have taken that outside, and since c is positive, I have u of p comma f comma alpha as it is. Okay, and if I take the c outside this, I have c into infimum of u of p comma f comma alpha. Why? Because c is constant, I have taken that outside. And since c is positive, it doesn't affect this infimum. So I have c into infimum of u of p comma f comma alpha. What is this infimum of u of p comma f comma alpha? It is nothing but the upper integral of f. Okay, so integral a to b by f d alpha with this c. So now I have integral a to b bar c f d alpha is equal to c into integral a to b bar f d alpha. So the upper integral of cf is now equal to c into upper integral of f. Similarly, lower integral, if I consider the lower integral, you will get like this. Okay, similarly, integral a bar to b c f d alpha is equal to c into integral a to b lower Riemann integral of f will be equal to lower Riemann integral of cf. Okay, so as we did here, we'll continue the same thing for this also. At last we'll get this. Since f and cf both are Riemann-Stieltje integrable, we have, see, in place of this I can simply write integral a to b f d alpha. Why? Because f is Riemann-Stieltje integrable. So in place of this I can write integral a to b f d alpha. And since cf is Riemann-Stieltje integrable, I can write integral a to b cf d alpha in place of lower Riemann-Stieltje integral. So similarly here also, in place of upper Riemann-Stieltje integrable, I can write integral a to b cf d alpha, and in place of integral a to b over f d alpha, I can write integral a to b f d alpha. So at last you will get like this. So using this definition, that is, since f and cf are Riemann-Stieltje integrable, so I can write integral a to b cf d alpha is equal to c into integral a to b f d alpha. Okay, now let's move on to the next case. What if c is less than 0? Okay, if c is less than 0, see here I will consider again the upper Riemann integral, so of cf, which is equal to infimum of all u's of cf. Okay, and now if I take the c outside, I will get L of p comma f comma alpha. Why? Because now the c is negative actually. C is negative. So, see, that is, if you multiply this c with this L of p comma f comma alpha, you will get this. Okay, if c is negative, then you'll get this. If c is positive, then you should write u only here. Okay, so if c is positive, then this u is unaltered. But if c is negative, then c into L of p comma f comma alpha is equal to u of p comma cf comma alpha. Okay, so now this can be written like this. And if you take the c outside here in the next step, then this infimum turns to supremum. That is, if you find what is c into supremum of this, then that will be equal to this. Why? Because c is negative. Okay, so this is nothing but the lower Riemann-Stieltje integral of f. This is the definition of lower Riemann-Stieltje integral. And now I have upper Riemann-Stieltje integral equal to c into lower Riemann-Stieltje integral of f. This is the upper Riemann integral of cf, and this is the lower Riemann integral of f multiplied with this c. So if c is negative, this happens. And similarly, lower Riemann-Stieltje integral of cf is equal to c into upper Riemann integral of f. Okay, if c is negative, then lower Riemann integral of CF is equal to C into upper Riemann integral of F. Okay, and since we know that F and CF belongs to R of alpha, I can have integral. See, in place of this I have A to be FD alpha, and in place of this I have A to be CFD alpha. And here also in place of this I have A to be CFD alpha, and in place of this I have A to be FD alpha. So at last I have integral A to be CFD alpha is equal to C into integral A to be FD alpha. Okay, so this is all about the proof. Thank you.